curvilinear coordinates. So the first step what I do is I write down the equation of continuity, the equation of motion in the cylindrical coordinate system. So what we will do is to take up the special case of steady flow of an incompressible fluid. So if we look at the collect together now the formula that we have derived and write first the continuity equation can be written as 1 over RC so instead of we already have to deal with RC because there's a subscript C and then on top of it I have to deal with BRC. For ZC, since it's the same as the Z coordinate, I will simply write this as dBz by Z. Well, replace ZC by simply Z to avoid having to write another quantity with subscript. So, if you look at the equation of motion, the RC component would have 2 times it also will be incompressible and linearly viscous fluid. All that is taken into account. Constant viscosity. And then I have that's the inertial term V dotted with the gradient of V, and on the right hand side I get minus dP by right here. Component. This would be dRC dV phi by dRC plus 1 over d phi times 1 over RC dV phi by d phi plus dRC by RC plus dZ dV phi dZ is equal to minus 1 over RC dP by d phi plus rho B phi plus 2 times again. I'm writing all the terms, and this would be d by d RC 1 over RC d by d RC plus 2 over RC squared. Long, wider expression. So, for Z, this would be dRC dV6 by dRC d phi by quite tiring for me and probably for you as well, is that the notation is sort of different from what is there in Wordsworth. Like, hopefully I've written all the terms correctly. We will double check that. What we are now going to consider is are the special cases of the so-called one-dimensional flow. It means only one of the components in the cylindrical coordinates is non-zero. All the previous assignment has been designed to give some examples of that, and I hand over another assignment which will have variations of these problems either tomorrow or latest by Monday, right? So now if I consider the three special cases of so-called one-dimensional flows in cylindrical. One-dimensional is somewhat misleading because we will see that if you consider some of these flows in the Cartesian coordinate, you will see that more than one component will be present. Because we have the VRC, right? That will have components along Vx and Vy. So what we call here as one-dimensional is only with respect to the cylindrical coordinate system. It will, if you solve the same problem in the rectangular Cartesian coordinates, then it will have two components, and that's one of the advantages of switching to a suitable coordinate system, right? So if I consider now, I consider three special cases. One is V is equal to VRC, and then the second case is V equal to V5, and then the third case is V equal to VZ. Let's see how these equations modify. So first, if you look at the continuity equation, d5 equal to dz equal to 0, then I am getting d by drc, the continuity equation. So it clearly shows that it's not drc that is independent of rc, but the product rc times drc that is independent. So these are some peculiar aspects of the curvilinear coordinates that you have to be. And similarly, if I put d5 equal to, drc and dz are 0, then we get the straightforward result that dp5 by d5 equal to 0. So when you look at the third one, dz alone is present, then we get the dvz by. This is coming from the continuity equation. We have to take that into account, and this will further simplify the equations of motion. So let's take, the third case would be the simplest case, right? So, but let's take each one of them one by one. So if we take VRC, so what will happen, right? So here, V5 is 0, right? So, and Vz is 0 in the first case. So the inertial terms, though, are not going to vanish all the time. That's what you have to be aware of, right? You have to carefully look at the inertial terms and figure out whether in each case they are vanishing or not. Because we saw that the three cases of one-dimensional flows in the rectangular Cartesian coordinate, it would be V equal to V1, the first case V equal to V2, V equal to V3. All three cases, the inertial terms vanish identically. Such will not be the case in the cylindrical coordinate, and it will also not be the case always in the spherical polar coordinate. So let's write the terms down. So clearly the inertial terms are not vanishing. In this case, rho v rc we have to deal with this term. They will cause complication in solution because they are non-linear terms. Okay? So that is why the problem is. So that will lead to minus dp by drc. So those terms are there. Now we see here that this term will now vanish because d by drc, rc, vrc is 0 by the continuity equation. When BRC is the only non-vanishing component, right? So that term will vanish, and then I will have to deal with the other terms which are there. So that would lead to plus the viscosity times 1 over RC. So this is 0 because V phi is 0. So 1 over RC square d square BRC by d phi square plus d square. Look at the other equations, right? If you look at the other equations, d phi is 0, so identity is 0. So all these terms now vanish. Right? The inertial terms are still in the case A. So the three equations are 0 into the second equation would be minus 1 over RC d by d phi plus rho b phi plus, if you look at this is 0. DBRC by d phi cannot be quite neglected. We seem to get that term. Right? So unless we make an assumption BRC is independent of phi, we cannot neglect that. So we get plus dBRC by d phi.
So for axisymmetric flow, it will be 0.
Yeah, so let's not worry about that now. I'm just writing the equations as they are. Right? So what I think this is what the equation motion tells me. Probably based on the physical situation, you can probably make further approximations and or simplifications. Right? So then if you go to the third term, third equation, right? The third equation dz is 0. This is entirely 0, and you will see that all the terms are all other terms are 0, and so we simply get 0 equal to. So this is all for A, 0 equal to minus E. I'm not expecting you to remember all this, but I just if you're going to solve the problems, it might be worthwhile writing it down. Right? So this is for case A, and so for case B, where E equal to B phi, right? So for the equation of motion, right? So this is 0, so you're going to get minus rho B phi square by, now I'm writing the RC component, minus rho B phi square by RC is equal to minus plus, what are the terms that are going to contribute? B of phi is the only component, then this is 0, and this is also 0 because BRC is 0. This is 0 from the continuity equation, so I am not getting any terms. That's all I have. So the RC component of the equation of motion, right? So then the second equation would be here B phi, so dB phi, so BRC is 0, and then again I have dB phi by d phi is 0, so that also will not contribute to 0. Really, note of Vz is 0, so inertial terms are identically 0, right? And then I have minus 1 over Rc plus, obviously, all the dB phi, since d phi is independent of phi, so this is 0, right? So I'm going to get again two terms plus times d by dRc of 1 over Rc, right? D by dRc of Rc d phi 1 over RC squared, that is term is 0, plus d squared d phi by dz squared. And then the third equation will probably be simpler. So dz is 0, so all of these terms are 0. Dz is identically 0, and so probably none of the terms would contribute, and I would simply get minus dv by dz equals rho dz. So all of these correspond to equation of motion for case B, which is only the phi component is present. Right? So if you write these equations down, then it's easier for you to solve the problems in the assignment. That's one of the reasons that I'm writing it. Because it's a fairly tiresome, procedure to see which of the terms stand and which vanish. Now the last equation you can expect to be very similar to the Cartesian case, because it's after all the Cartesian coordinate z, right? So if you look at that, this will be entirely 0, and so would this be no contributions at all from any of these. So that is the simplest case. We will first take up, that's not there in the assignment sheet, this is standard problem of flow through a pipe. Right? And then this again, all the inertial terms you can easily verify to be 0. Even the viscous terms would be 0. So I would get 0 equal to minus 1 over RC. And then the third equation obviously would be the most important equation relating the velocity. Again, this inertial terms are 0 because dz by dz is 0 by the continuity equation. The inertial terms are 0, and then I have, obviously I will have the viscous term, so minus dv by dz plus mu times dz by dz is 0. So dz is independent of z, that's what it means. So because these are identical relations, valid at all points, dz is independent of z. I'm not saying that just because dz by dz is 0, d squared dz by dz squared is 0. It's not a universal rule, but here dz is simply independent of z. That's what this means. It's not just at one point that this holds. It's valid at all points. So dz becomes independent of z. So all derivatives of dz identically vanish with respect to z. Right? So this term would be 0. So the viscous term would have two terms, 1 over RC plus 1 over RC squared. So that second term is usually neglected or discarded in the flow to a pipe. So let's now take erase all this because we've simplified it for our immediate purpose. So hopefully the effort of writing the equation started and then we wasted. I'll very quickly go through the flow through a pipe because I can bring the importance of the pressure on incompressible fluid. That's the only reason I'm doing this. The flow down, this is what virtual making considers. Go down a circular pipe, right? So this is the flow, and we can take this to be the origin, for instance, and so the z direction is going to be the downward direction. All other directions are and phi, RC and phi are as. So the radius of the cylinder is taken to be capital R. So the equations are there already. So these two equations will imply that VRC, because this is taken to be the z direction, right? So the V itself can be written as V times Ez, right? So we are taking the downward flow direction as a positive z direction, right? So there are no components of the body force in any of the other two directions, so that would necessarily mean that the pressure gradient. So these two equations would imply that the P is simply a function of Z alone. That's what I get out of those two equations. So the inertia terms all vanish, and the way I have chosen the flow direction and the Z axis means that the components of the body force in the RC and phi directions are zero. What these equations then imply that the pressure derivative with respect to RC and phi are zero, and so P is a function of Z alone. Right? So now Vz, of course, is simply G. So if I write the equation of motion in the Z direction, then I get 0 equal to, and I can now write this as minus dP by dz plus rho times G. Right? Because that's the only component of the body force. And then it is conventional here to neglect the dependence of Ez on phi, the standard derivation of the so-called Hagen-Coaxial equation. That's what we do. that is not allowed under physical considerations. So we assume or we infer from, not assume, that C2 is actually equal to 0. We can make that inference right away, right? So when C2 is equal to 0, then Vz would be C1 by Rc squared by 4 plus I can call C2 prime. Some other constant. We get another integration constant. Right? We get another integration constant. And then how do we calculate? So one of the integration constants can be determined by using the no-slip boundary condition. When you look at the fluid, we assume the fluid wets the surface of the cylinder. So that would mean that Vz equal to 0 at Rc equal to R. So we get V0 is equal to C1. See, this doesn't denote derivative. It's confused like this C2 bar. Right? So C2 bar is actually minus C1 by 4, and so the Vz can be written as C1 by 4 minus C1 by 2 times R squared minus Rc squared. So what do we do about C1? The C1 is given by this, so I have to get it from the question. Get it used. Usually it is expressed as in terms of the pressure difference, the pressure-driven flow. So if I now look at this, so dP by dz minus rho g is equal to C1. If I now integrate this, right? So I get P minus rho dz is equal to C1z, which means not just that, plus some constant. Let's call it E0. Right? So, which implies that P is equal to C1 plus rho g times z plus P0. P0 is clearly the pressure at z equal to 0. Right? I can now introduce that can be given, assumed to be given. So if at, let's say at a length L, the pressure is known, right? So P and L, we will call as PL, is equal to C1 plus rho G times, because I still need C1. The whole point is that the C1 is left undetermined, right? So we now see that to determine C1 unambiguously, we need to know the pressure actually at 2 points. So there is an integration constant coming from the pressure, and there is an integration constant, 2 integration constants coming from the velocity integration. So the total 3 constants that have to be determined, right? And so one of the constants we determine using the no-slip boundary condition. So C1 is one constant that is not known yet. And when I try to get it from the pressure equation, I get another integration constant. Obviously, because it's the first order differential equation, the pressure. So now we have to deal with effectively 2 constants, right? So if I now introduce, let us say that if I know the pressure at z equal to 0, then I would know one of them. So still C1 is left. So to know C1, I need to effectively argue, I can argue that I need to know the pressure at another point, right? So then that would be naught, and so C1 is then given by, right? C1 is given by PL minus P naught minus rho G L, right? So what words could
PL minus P naught by L minus L minus PL minus P naught by L minus rho G out of the distance
minus rho G L by L. I can write it like that. Right, so I can write it like that. So what is conventional to introduce what is called as a modified pressure, and words will like to do it repeatedly. Something called as a modified pressure, which takes into account the effect due to gravity. Right, so I can now introduce a new variable P, define it as, I have to define it suitably. P can be defined as P minus rho G Z. That's the modified pressure, right? P minus rho G Z. If I introduce that, then C1 can be written as PL minus rho G L would be PL, right? Minus P naught, but minus rho G times 0. That can be also written as P naught, because that descriptive P naught is simply P naught minus rho G times Z equal to 0, right? Because that's the modified pressure at Z equal to 0, and you have the modified pressure at Z equal to L. So the C1 can be conveniently written as, in terms of the modified pressure, right, difference between 2 points divided by the distance between the 2 points. Then I can now write this. So I need minus C1, right? So I can write this as P naught minus PL by this. So this is the most important relation. Relation, and it is given as if this can be regarded as a pressure drop. This is the pressure, the modified pressure drop, right? If that is positive, then it leads to a flow in the Z positive Z direction. That's how you have to view it. The whole velocity profile is given in terms of the modified pressure difference per unit length, right? And of course divided by viscosity and so on, like times this. So to the parabolic velocity profile that you are all familiar with. Now the flow rate, mass flow rate can easily be, by calling it n dot, is given by our nr maybe. Is integral rho b dot at the n dA, and you can easily use the fact that it's a one-dimensional flow, right? The flow is in the you have to be careful. If I'm looking at it as inlet, this will give me the mass. If I focus on this is giving me the mass efflex actually, right? So mass inflex here at the top. So you look at the entry. If you focus on the entry, I have to make it minus rho b dot at the n. So rho b dot n is the outward normal vector, right? If you don't take care of this, you will get an answer which is negative, which of course doesn't make any sense. So the flow rate has to be, it's a scalar, right? So we can adjust the negative sign suitably. So here I'm looking at this, look at the entry point here. This will give me the mass efflex, right? Rho b dot at the end. So if we want the mass inflow, then I have to put a negative sign, right? And then the negative sign is there. So rho bz ez plotted the n, the outward normal, right? That is pretty much the xy plane only. The outward normal for this phase would simply be minus Ez. You can see that is taken care of. Right? And what would be dA? Right? So this is the normal to the constant z surface. You can either by geometry, simple geometrical arguments, or by the means of the metric coefficients that we have. So that would be RC, d phi, and you get the metric coefficient would be RC. This is very standard for cylindrical coordinates, so you probably don't even need all those abstract developments. So this will lead to the, so if I now do this, I need to, this is a double integration. So this is going 0 to R and phi varies from 0 to 2 pi. There is no dependence of Vz on phi. So the 2 pi can be taken out, right? And then that the integration over phi would simply be 2 pi. If you do this integration, you will get the, and divide by rho, you will get the famous expression for the mass flow rate, which is the, has a fourth power dependence on the radius of the tube. Right? So these are well-known results. The famous Hagen-Poiseuille equation. We just derived it here using the equation of motion and the basically for the linearly viscous fluid. Right? So, are there any questions on this? The important thing is the role of pressure. So the equation itself is given in terms of the pressure difference comes as a parameter actually. So we have to provide that to calculate all of this, the velocity profile and the mass flow rate. Right? So if there are no questions, we'll move to the next problem, which is the problem given in the assignment, which deals with the rotation. That's an important standard problem worked out, the simpler cases worked out in Stewart, Lightfoot. That is the second problem. We give space between two coaxial cylinders is filled with the fluid, and the fluid is now rotated. Both the cylinders are actually rotated. So the hollow space between two cylinders, the annulus between two cylinders is filled with the fluid, and in general I can rotate the inner as well as the outer cylinder at different speeds. You can consider various special cases where one of the cylinders alone is rotated and another is not, and so on. Right? So I am actually now have to make use of based on the rotation in Stewart, Lightfoot. This is the two cylinders, right? And if I take this as the axis, and here Stewart takes this as the z-axis, the positive z-axis, let's say from the bottom of the cylinder, right? And as per this notation, the radius of the outer cylinder is given to be capital R, and the inner cylinder is given to be some kappa times R, which means kappa is clearly a quantity which is less than 1, right? So the fluid is rotated. So the rotational flow we assume to correspond to, this is not to be confused with the rotational flow that is commonly used where the curl of the velocity of vector field is non-zero, but this is rotated, so it's assumed that this corresponds to the case B, and we can safely assume that significantly the radial components and the z component will not be there. Right? This is a standard assumption. The dominating velocity component would be V phi. So now we directly go to these equations, right? And so we have these three equations already written down, right? For the case of, so we have to now deal with the inertial term. This is important, right? And subsequently, you are asked to repeat for the case of two concentric spheres, and there you will find the answer given in Stewart, Lightfoot will be obtained only if you neglect the inertial terms for the spherical case. Here we can solve it directly as we will see. Right? So this term will be there. So PRC is clearly again 0. So here actually B is minus D times Z because of the choice of, and forget exactly the in fact virtually it has worked it out for a single cylinder filled with fluid. Right? So I'm just going to follow the procedure he is given there, the assumptions he has made, and the notation he is given there. Right? So this will be 0 and this will also be 0. Let's now look at the other terms. Right? So dp phi by all those we've already taken into consideration, and so this is going to give me some contribution, and further assumptions are made. If you look at again the this is of course known when Bz is minus G. Because here we have chosen the upward direction as this positive Z direction, right? So here person tries to further gets rid of this term, which is not generally 0, but he says that can be neglected, and he also neglects this, the pressure variation. Now let's look at the pressure variation. Pressure variation here, and I can easily integrate this. When I integrate this, what I will get is dP by dz is equal to minus rho g. I cannot do anything about this yet because it depends on d phi. D phi is not yet found. So all these simple, you might wonder, how are we to know what are the simplifying assumptions that you would have to make in a particular case. I will come to that question later. For now, I am just following the arguments made in Stewart, Lightfoot and neglecting certain terms. dP by dz equal to minus rho g. I can integrate this. P is equal to minus rho dz plus, right, a function which in general can be a function of both Rc as well as phi. In general, just an integration, a partial differential equation in Z, right? However, by taking this assumption that dP by d phi equal to 0, I can make this as some function of Rc alone. So the argument given is that what the Lightfoot argues is that here the pressure variation in the Rc direction is sort of given by the centrifugal acceleration or centripetal acceleration, and here it is the dependence of the pressure on Z is given is provided, the pressure gradient, the Z direction is provided by gravity, whereas here it is provided by the rotational motion. Whereas there is no reason to expect there is anything driving the pressure gradient in the phi direction. Of course, you can argue there is a viscous force, and you can regard it as a balance between the viscous force and the pressure force in the phi direction. But he simply says that there is some physical arguments, right? There is nothing physically to drive the pressure gradient in the phi direction, and so he neglects that. Basically, the point is, to get the answer he has, we have to take all these other simplifying assumptions, right? So with that, the problem can now be solved, and we run out of time. The boundary conditions are important now. The two no-slip boundary conditions, but now important to note is that the domain is actually between. So the radius is actually lying between the domain of the differential equation. Basically, is between these limits, right? And so we take up the solution tomorrow. So the boundary condition will change according to that. These are the two boundaries basically. R equal to Rc equal to kappa times R and Rc